Welcome back. Let's continue our discussion with the most common tree data structure. That is the binary search tree, which is a subset of binary tree, which we talked about. What is a binary search tree? Well, a binary search tree are really good, as the name suggests, at searching. They're great for comparing things. Now, why would this be better than, let's say, a hash table where we can just give it a key and get the item right away? Well, this data structure preserves relationships. Just like you wouldn't want your folders on your computer to be in a hash table data structure because there is no sort of relationship. Instead, you want your folders to have relationships, to have a parent folder and a subfolder and then a subfolder. A thing like binary search tree allows us to preserve these relationships. When it comes to binary search trees, these are the rules. 1. All child nodes in the tree to the right of the root node must be greater than the current node. That means if I keep going to the right, the number or the value of the node constantly increases. You see over here, I go from 101, 105, 144. If I keep going to the right, let's say here, 33 to 37, that is increasing. If I go to the left, 101, 33, 9, that's always decreasing. Same with here, 105 to 54. If I go to the left, it decreases. To the right, it increases. And then the second rule is that a node can only have up to 2 children because it's a binary tree. The advantage of a binary search tree is that, well, it should be obvious with the name, right? Searching and lookup is very easy to find what you're looking for because if I'm looking for, let's say, number 37, I can start at 101 and say, is 37 less than 101? Yes. Okay, then go to the left. Is 33 less than 37? No. Then go to the right and I find 37. I don't have to iterate in a linear fashion through each node. And that is what lookup means. Lookup simply means that I can search for an item a lot faster than, let's say, an array where I have to iterate and loop through every single item. But what about insert and delete? In a hash table, I can do insert and delete really fast at O1 or constant time. But with a binary search tree, it looks like I can only do O log n. And that should be obvious, right? Because in order for us to insert or delete something in a binary search tree, we need to figure out where to insert the item or where the item is before we delete it. For example, with 105, let's say that we want to delete 105. Well, we have to first, from the root node, get to 105, and then we have to decide which node is going to take its place. In this case, because 54 is less than 144, 144 is going to come up over here. But as you can imagine, this operation, although seems simple right now, if we had a lot of children and a lot of nested nodes, a lot of reordering needs to happen and shift our nodes around. And don't worry, we're actually going to code this so you understand this just like we have in previous data structures. But I want to demonstrate, instead of me just using my cursor here, a nifty little tool to visualize how binary search trees work and how their operations are O log of n. We're going to use Visual Go again, and I'll link this, and I highly recommend that you all play around with binary search trees. But let's do a couple of operations here. See that it generated a random binary search tree for me. Let's say I wanted to do an insert, and I want to insert, let's say, the number 1. If I click Go, it's going to traverse, figure out where it wants to insert, and it's going to insert 1. What if I want to insert perhaps number 44 this time around? If I hit Go, it traverses, figures out where 44 should go, and places it down here. So we're always traversing and figuring out using O log n where we should place the item. What about removing? Let's add one more. I'm going to insert 51 this time so that it places it right over here. Perfect. Now, let's say we want to delete 50 now. If I remove 50, I hit go. I find 50, remove it, and then I have to replace with 51 and go up. So there's a bit of a tough little logic happening there that we're going to have to incorporate. And we're going to get to that. But for now, as I end this video, I recommend that you go to Visual Go and play around with binary search tree so that you get accustomed to it. And as you play with it, see if you notice a problem that we might encounter with binary search tree, because we're going to discuss it in the next video.